Okay, now we're going. Okay, so I hope that we're going to be able to, I hope that I'm actually going to be able to tell you what a neural network is, but we may not be able to get there today, right? But I can tell you about a bunch of other stuff that is equally interesting, that are all things that you'll need to understand to eventually understand neural networks. Okay, so I have to mention beforehand that we're going to be looking at, so a neural network is a type of machine learning. And there are two different types of learning. There's unsupervised learning and supervised learning. And supervised learning is the easier type of learning. So I'm going to be teaching you about the easier type of learning today, right? That is the supervised learning. So I'm going to talk about three things, right? Linear regression, logistic regression, and neural networks, right? A neural network is basically just a sophisticated combination of linear and logistic regression. And don't worry, I'm going to describe them like really precisely. So you'll understand what they are. Okay, before we talk about anything, I just want to lay out all the notation I'm going to use for the rest of the talk, right? So this all looks very complicated, but essentially all I need some input, and I need to label that input. So like maybe I have like house attributes and price, right? Okay, maybe I'll go to this slide. So I need input, I need a label. Right, so in this case, I have square footage of the house and how old the house is. Those are inputs. The value of the house is called the label. Right, so these are called features. These features are collected into vectors called inputs. And then the inputs are associated with labels, which are called y's. And then I'm going to collect all of the inputs with their labels into pairs, right? So I have these sort of feature label pairs, which I'm going to collect into a set called data, right? So basically, I have a bunch of data which are features associated with values, right? So this vector x to the funny bracket I is notation for the ith input. Right? The ith input is going to have label y bracket I. We use bracket I just so you don't get confused and think it's exponentiation, that this is like a label. So this D is going to be a sequence of n finite many data pairings, and we're going to group input points with their respective labels. So I'm just going to basically run through D like our for loops. I'm going to say for some x, y, and d. I'm going to pull out one of these data points. So here's our problem statement. Given some data, like housing prices matched with square footage and age, I want to learn the parameters to a function, which I'm going to call the prediction or hypothesis function. So the idea is that you give me a bunch of data, I learn a function that represents that data, and then I use that function to generate guesses for new pieces of data that I don't have labels yet. I want to assign new labels. And somehow it's going to be important that this function is convex, but it all becomes a lot more clear when I start showing you diagrams. Okay, so the goal here is, given this table, right, I want to learn a function which is going to let me predict values for new houses, right? So I somehow am able to learn over this table, and that I may find out that I've generated a hypothesis function h that tells me that a house of 2,000 square feet that's 5 years old with our learned parameters is worth $300,000. The thing that you have to note is that the hypothesis function that you find may be off for like known values, right? So I may train a function, a hypothesis function on this table, and my hypothesis function may say, oh, a house that has 1,500 square feet and is 17 years old is worth $200,000, even though the table says it's only worth 150. Right? So the hypothesis function isn't going to report, it's going to be off, right? It's our best guess, right? Even though the data would say otherwise. So you may be more familiar with this problem stated like this, right? Given a scatter of points on a plane, find the line of best fit, right? If you've ever done that before, congratulations. You've implemented a machine learning algorithm. Right? Machine learning, neural networks, these are all big buzzwords of it. These are old techniques. We've had these techniques for like 100 years. Right? They've just somehow become popular and renamed to give them more sexy names. But whenever you hear neural networks or artificial intelligence, you can just replace that in your mind with applied statistics. Right? Because that's all we're doing. Okay, so a line has two parameters, right? The y-intercept and its slope, right? So when I say I need to learn, when I say I need to find the line of best fit, that's equivalent to saying I need to learn the parameters of a line that minimizes error through that scatter plot. To make things more easy in our deduction here, I'm going to assume the line is passing through the origin. What does that do? Well, it allows us to assume that our y-intercept is 0, right? Which means that we only have to learn one parameter, the slope of the line, right? So this is called actually normalize. You do this really in real life. You're given some data, and then you want to recenter it so that like everything is around 0, so you can drop one of the parameters, right? So not only is this useful for like deduction, it's useful practically because it reduces the dimension of the space that you need to learn in, right? Learning one parameter is easier than learning two parameters. Yes, yes? Huh? Sorry? I didn't label the axis, right? So it's your assumption that the intercept, that this point here should be at 0, 0, but I didn't label it, right? So it doesn't matter. I'm just saying this way is the x way and this way is the y way, but yeah. So that's a trick that you can play on your math teachers. If they ever say draw something, just draw it and then don't indicate, like don't draw in any type of thing on the axes. And you just say, well, I didn't label it, right? So you have to label it, then you'll find the right answer. I've done that, and I won, because it was technically the correct answer. Okay, so anyways, I'm showing you a scatter plot on like a plane, but there's no reason I can't show you a scatter plot in 3 dimensions, except that I'm lazy and I didn't want to generate it. But 4 dimensions, 5 dimensions, 6 dimensions, I properly can't show you that, because those are beyond dimensions that we as humans can perceive. So this is sort of the whole purpose of mathematics, right? Is to enable us to talk about objects that humans can't visualize. So it is not only the case that we can find the line of best fit, it's more appropriate to say we're finding the hyperplane of best fit, right? A line is a hyperplane in 2 dimensions. A plane is a plane in 3 dimensions. So really we're trying to, like, the reason we care about linear objects is because they're super easy to construct, right? So we're just trying to find some line in n space that fits our data somehow, right? So we're going to talk about how to fit that slope to that scatter point, but generally speaking, I should be showing you a deduction about how to fit a hyperplane in a surface. But it's the same concept, just a little bit more sophisticated. Yeah.
Is the hyperplane always one dimension less than the dimension it's inhabiting?
Depends how you define dimension, right? What is the dimension of a line?
If we're plotting in 3 dimensions,
yeah.
The hyperplane is going to be a square.
It's not going to be a square. It's going to be, you pick 2 directions, and it's anything that you can reach walking in those 2 directions. Right, so I don't know what the dimension you'd, so that's a dimension 2 object embedded in 3 space, right? But it's still a 3 space object. So it depends what you mean by dimension, right?
It has to be infinite in both ways.
Well, all lines are infinite in both ways, right? So on a plane, you give me 2 directions, or actually you give me 1 direction, and that defines the line, right? In 3 space, you give me 2 directions, and that defines a line, a plane. In 4 space, you give me 3 directions, right? So, anyways, take my math class, we can talk more about this. But in any case, so the question is, how can we learn the parameters of a hypothesis function? When I say learn the parameters, you can think in your head, how can I learn the slope, right, of the line that best fits that scatter plot? Okay, so what I want to do is let's just pick any slope for the line. And then let's say, how wrong is this line? Right, so we need to quantify wrongness or error, or what the machine learning people say, cost. What is the cost of setting the slope like this? And then once I can quantify the cost of setting a certain slope, then I can say, okay, minimize the cost somehow, and then the slope going through the points with the minimum cost is the one that we should choose. So how can we talk about cost of fitting a line to some points? I'm going to show you 3 ways of describing it. The first is the easiest. If this is so the blue points here are is the data, is the stuff that we went into the field and collected. The magenta line here is the line that we're saying is the line of best fit. So I'm just going to say the error is the distance, right, squared between what our guess would be and the actual value, right? So, because again, this line is saying these are the values, right? These are where values are going to lie, and we're off a bit, and we're off exactly by this error. So another way of saying that is, okay, so I have my jth input, and it has this yth label, right? This is y hat is the guess, right? So for the input xj, I guessed that it has this y hat label, and in fact, the real label was yj. Right, so we have y hat, which are the guesses, and y without hats, which is the observations. So the difference between our guess and the observation squared is going to be our error. Okay, so this is an easy way of describing it. This is a less easy way. This is the least easy way, which happens to be the one I want to take. Okay, so here we're at point. Suppose this is the point of input x1 with its label yi. So this is the ith observation. So I take the ith observation and I send it through my hypothesis function, right? My hypothesis function is the line, right? So I give it an x and it should spit back a y, right? So given an input and the slope of a line, I can then tell you, I can quantify the error of that line by summing how far my line is individually from each of the observed data points, right? So this is called the quadratic loss function. So I'm going to work this out for you a bit, right? So I'm going to call our cost function j, right? Because that's what the data scientists do, so I'm just trying to use their notation. Okay, so you tell me what the slope of the line is, and then I have to tell you what the error associated with choosing that slope is, right? So as I said, you want to go through all the data, right? So this is like a for loop in Python, right? For x, y in our data, I want you to look at the label for I, and then guess a label for I, and then find the squared difference between those two things. So I can write it like this. So if you find a slope, you give your slope to the hypothesis function, which sets the line, and then I run through the data and I just sum all the errors along all of the data and square it. I can simplify this expression because this, again, is a hypothesis function which is just a line through the origin. So I can replace that hypothesis function with exactly what it is, which is the line through the origin with slope theta 1. If I square this, I'm left with this expression. Now, I don't care really about this deduction. The only thing I want to demonstrate to you is that in this case, the cost function is a quadratic polynomial in theta 1. Right, can you see that? Right? If I do this sum, right, I don't know what theta is. Theta is a free variable, but I do know what my x's are and I do know what my y's are. Those are going to be actual values. Right? So I give this to the computer and it spits out a polynomial, right, with some weird coefficients, weird float coefficients. And that is going to be our cost, right? So the fact that it's a convex quadratic polynomial is important. Let me show you why. Okay, so remember, so this is the cost associated with choosing a line, right? So along the bottom here is slope, right? And along the y-axis here is cost, right? And I didn't label it, so this isn't necessarily the origin or elsewhere, right? So where would be the best, what's the best theta to choose here which minimizes cost? Yeah, you want to find the lowest part of the parabola, right? So there's a technique which is super important called gradient descent, and it works sort of like this. Imagine you take a ball and you drop it into the parabola. It's going to do this, right? The ball's going to rest at that point, okay? I was telling this to my calculus kids the other day because I don't think they understand that calculus is important. But it's important for this. I'm going to teach you the world's simplest algorithm. Okay? Pick a point on the curve. That one. Okay? What's the slope there? Oh, it's positive. Okay, if the slope is positive, then move left. I've moved left. What's the slope here? Oh, it's negative. Okay, if your slope is negative, move right. Negative, positive slope, move left. Negative slope, move right. You found it. You can go home and implement that right now in Python. It would take you 5 minutes. Right? But that's all. If you have a parabola, that's how you find the lowest point. You pick an arbitrary point on it and move left when the slope is positive and move right when the slope is negative. Bonus point. You can actually move by some, like you can move proportional to how big your slope is. Right? Because if you're like way out there, your slope is going to be enormous and you should move left a lot. Right? Because generally at these points of minima, things are going to look flat. So you should be expecting that the slope is getting closer and closer and closer to zero. See, calculus is important, including for you computer scientists. Okay, so that was fitting. So you can see then how I could take that gradient descent and apply it to that line to find the fit. And I'll show you how to do that soon. But one of you should have complained. You should say, well, this is really in the most trivial case where like I'm just spinning a line in points. Suppose I didn't want it to go through the origin. Suppose I wanted to train two things, right? The y-intercept and the slope. Then I have two parameters I have to train, two slope parameters. Then you say, well, what do I do then? Well, turns out gradient descent works in all dimensions, right? Provided that the function is convex somehow. And what I mean by convex is that if you threw a ball into the surface, the ball would eventually like settle in like one of these wells. Right? That's basically what convex means. Like for us, convex means that we're going to be able to find some minimum part of the surface. Right? So this is how gradient descent works on a surface. You start at a point on the surface and you find the gradient. Now the gradient is the same thing as finding the slope, essentially, except that you also have to like give me a direction. Have you guys taken vector calculus yet? The gradient is just the slope in both cardinal directions. You tell me what the slope is north, and you tell me what the slope is east, and that actually gives you like a direction, right? So you'll learn about how the slope generalizes. But suffice it to say, if you're on a surface, I can find the slope, and it ends up being a vector. And in this case, it's telling you to move this direction. So I move from the top of that hill where the point tells me, and then at that point I find the gradient again. And the gradient tells me to go in that direction. So you move it to that direction, you go to that point, and you find a new gradient. It tells you to move to there, and well, and that's it, right? So this method also works in higher dimensions, right? So we can reuse gradient descent beyond 3 dimensions. We use gradient descent to train hyperplanes in arbitrary dimension, and I'll give you the equation to do this. Oh, here it is, right? You could write this, right? So repeat this, right? So you just make some random guess on theta, right, which is basically puts you onto the surface somewhere, and then you just do theta minus alpha, the gradient, right? So you just walk in the direction of the slope. Is basically what that's saying, right? So this is the update routine for gradient descent. So like, it's amazing such a useful algorithm is so compact. Right? This isn't 3 lines. I'm saying, well, it's this, right? So there's 2 ways of describing it. So it's either a vector comprised of all the partial derivatives, but that ends up just being the gradient. So don't worry about too much about this, because you'll take some vector calculus and learn that it's not that difficult. I can actually go and do this, right, for the case that we're working on. Don't worry about how I calculated this. It's just there for anyone who'd want to go home and try and program this. But suffice it to say, here are the equations that I plug into that algorithm to do the gradient descent for the problem I'm talking about. So if I go home and I implement this, and I set a line through 0, 0, and I start it with slope 0, the cost associated with this is 116.3. That I actually did calculate this with a computer, right, for those points. So on iteration 0, if you choose this line, the associated cost is 116.3. After 1 step of gradient descent, it learns a better parameter. It then says, okay, I found something better. The cost now is 75.8. You let it do another step of gradient descent. It goes, oh, even better, 18.3 cost. Oh, even better, 8.8, 7.8, 7.6, right? So eventually, the cost is just going to start doing this. It's just going to, you're going to converge on some minimum cost, like 7.6, 7.7. It's going to just do this, right? So you run this until you get some type of nice convergence, and then you're done. Yeah. Yeah, that could happen. All right, so then you have to use higher order techniques, right? Because it is true that there could be several minima on a convex curve. But then you're finding local minima, right? So even those would be okay answers, right? But finding the global minimum, yeah, it's a different story. There's numerical analysis. That's sort of the whole purpose of that discipline of mathematics, right? Right, because we always teach you how to like work out these equations on paper, but it's like very rarely are you able to work out like NASA's not over at NASA like working out like equations to stuff. It's all numerical methods, right? Okay, don't worry about this slide. If you want to go and implement gradient descent, this is the slide that you need, right, for implementing it in n dimensions, right? You need to understand what a partial derivative is, and if you do, go crazy. This is the slide that you need. Okay, so that was linear regression. So linear regression is learning a line or hyperplane that best fits a collection of data in n dimensions. The second thing I want to talk about is logistic regression. So logistic regression is a little bit, well, it's a lot different, right? So in the first example, we had an indefinite number of labels, right? The labels were house prices. There's an arbitrary number of house prices. For logistic regression, I want to restrict ourselves to exactly two types of labels. In and out. True or false, 0 or 1, right? I want to restrict ourselves to a binary classification. And this time, instead of making a guess of a label, I want to say, I want to return a probability, right? You give me some data that has classified the data into two categories. I want to learn a hypothesis function on that separation. And then given a new piece of data, I want to say something like, I'm 80% sure that this new piece of data should be in this collection and not this collection. Right? So for logistic regression, I'm trying to learn how to divide data into two pieces. So this is the canonical example of logistic regression. Handwritten digit recognition. Have you ever thought about this? If we gave you an assignment that said, I'm going to give you a 16 by 16 bitmap. A bitmap is just a collection of, you can see that picture as a matrix, right? And where all the blacks are is a black cell, and where all the whites are is a white cell. So that's essentially a 0-1 matrix. So imagine we gave you a problem that was given a 0-1 matrix, determine what digit it is. You think you could come up with an algorithm for describing a 3? It's not, think about it. Think about how you would go and write a Python program to detect if something was a 3. This is not going to happen, right? Because there's no rule, right, about how a 3 is drawn. And your 3 may be different than your 3, may be different than the 3 that a 2-year-old writes. So this is what logistic regression is used for. Do you know? Anyone have any guess who invented handwritten? This was utilized back in the 70s. Any guesses who invented it? Who would be highly benefited by recognizing handwritten digits? Right direction. Even more so than that. Huh? The post office. The post office has a huge incentive for converting handwritten stuff into computer written stuff. Because otherwise some human has to read the address and route it. Right? So the US Postal Service, or a mathematician at the US Postal Service, invented this technique. Right? So when I say I'm going to give you a bitmap, you need to think of, oh, you're going to give me 256 bits of information. Right? You're going to give me 256 zeros and ones, which is going to be my new data. So my data now is 256 features, which is the blackness of the ith bit in the bitmap. And the label is going to be the label, right? So this is why this is supervised, right? In the first place, you needed a human to say, this is a 9, this is a 2, this is a 3, this is a 9, right? You need like a set of ground truth data in order to train. So you need a training set. I'll be happy if we can even get through logistic regression. So the purpose in this case now is not to guess at like a price, but to give a probability back. And generally speaking, if you don't train a hypothesis function which is greater than like 1/2 confident that something's in a set, then it's useless. If you only have 2 categories and I give you a new element and you're like, I'm 50% sure that it's in that category, that's worse than useless information, right? So in the very least, you need to be greater than 50% positive. I'm 51% positive it goes here. Well, okay, at least that's actionable, right? At least I can put it in there and be like, well, all other things considered, that was my best chance. Okay, so it's going to look like, our hypothesis function is going to look like this now. You give it a new bitmap, right? Something that's not labeled. You give it theta, right? You tell it how to set its parameters after learning them. And then this is going to be equal to the probability that this 3 should be given the label 3. And that better be greater than 1/2. Right? So in this case, the thing that we're trying to learn are the parameters to this probability function. Here are 2 pieces of data, the pink data and the blue data. All right? The hypothesis function needs to sort of find a boundary between those 2 pieces of data. In this case, since we're working on a plane, the boundary between these 2 things is going to be a line, right? And it's going to be a line parameterized by 3 things, right? We need three thetas to give this line, right, on x1 and x2. So the question is, right, so I'm telling you how to cut data into 2 pieces, but my first example was like 10 things, right? So is it possible to use, like, to be able to cut a set into 2, can I use that same method to like separate something into 10 pieces? I think about the digit example. I'm not framing this properly. How about if I give you a picture? All right, so I'm saying, look, I need to like find decision boundaries here, but I can only use 1 line. Well, I can say, this is the decision for being included in pink, right? You're either in pink or not, right? You're either in green or you're not. You're either in blue or you're not, right? So this is how I can use multiple decision boundaries to like actually categorize into many pieces. Because I can ask the question, well, is it in the blue or is it not, right? In or out. So I can just say in and out for each individual category. Right? Okay, so our first hypothesis function was the line, and the error associated with that line was simply the quadratic loss. That was easy, right? We're just running through all of our data and asking how far away from the line we are. The new hypothesis function is going to have to be a little bit more sophisticated, right? Because our hypothesis function now has to return a probability, and probabilities have restrictions. Like for one, the probability that will return better be between 0 and 1. Right? You can't have a -2 probability of being in a set. You can't have a 1.9 probability of being in a set. The second thing that it has to do is, if our guesses, because we're training something, right? So we need to reward the hypothesis function for improving. So if our guess is good, right, then somehow the probability of assigning something into a set has to get to 1. Right? So as our guesses get better, the probability has to also get better. Right? Our confidence in our guesses have to get better as our training gets better. And the other opposite has to happen. If we have a bad guess, the probability of guessing, if something's not in the set, then our hypothesis function better tend to 0. Right? So I have a piece of data, and as I'm training, if the thing's supposed to be in, when I train on this piece of data, we better tend to 1, and if it should be out, we better tend to 0. So there's this thing in calculus called the sigmoid function, and it's useful for this reason. It's a function which satisfies all the conditions that I just listed on the slide before. Right? It's a function which tends to 1, tends to 0, and goes all the way in between. Right? So I'm going to use the sigmoid function as our hypothesis function. Right? So basically, I'm going to give the sigmoid function a boundary, the boundary line, and then the sigmoid function is going to spit out a probability. And I'll tell you why that works. Imagine this is the line of the boundary between two categories. Okay? This is where things may get dicey. Do you guys know what the dot product is? Right, the dot product is you have two vectors and you basically just do the pointwise multiplication and then you add the results. Okay. Geometrically, what this means when you take the dot product is that you're getting the length of the projection of the dot into the line. And you guys must have done projections in high school. So you have a line. You're asked a question like, how far is this point from this line? I'm sure you're given that if you took the linear algebra course in high school, right? And the distance is called the component, right? So the distance from xi, right, this piece of data, to the decision boundary, the dot product is the length of that segment here, okay? So if this is a decision boundary, think of if this is a boundary between two sets. If I have a point, what should be true is the point is farther away from the boundary. Like, what should my confidence be? Huh? This is the boundary. Here's a point that should be in the set, and it's really far away from the boundary. I should be highly confident in that if, like, the boundary point is here, and you're way over there, I'm like, yes, you're in the set. I'm highly confident that you're here. Because conversely, what else is true? If I'm very close to the boundary, right? And I'm not even sure that my boundary has been set properly, right? So points that are close to the boundary, I should be uncertain about, right? So being close to the boundary is bad, right? That brings in uncertainty. Being far away from the boundary is good, right? Because you're more sure that it should be included in the set, right? The stuff on the border is really where all the uncertainty is. Well, provided that we set the boundary correct in the first place, right? Okay, so I have the sigmoid function. I give it a line, which is really telling me the distance to the boundary. And as I move further from the boundary, the sigmoid function tends to 1. So the farther away from the boundary I am, the closer my probability gets to 1. And the closer to the boundary I am, the closer my probability gets to 1/2. Right? So as soon as I'm on the boundary, my guess is going to be 1/2, which is I don't know. It could be either way. Right? You're right on the boundary. Okay, so now we have a hypothesis function. So now we need to ask ourselves, what is the cost for setting the parameters on a hypothesis function, right? Because we have to train the hypothesis function somehow, right? You have to give it the boundary line, right? So given that we've set some boundary, what now is the cost associated with this? And as soon as we get the cost, then we can use gradient descent to minimize things. So our cost function should steeply penalize bad guesses, right? So especially ones made with high certainty. If I'm saying, oh, I'm 90% sure that this point is in the blue category and you're wrong, the penalty for that should be steep. On the other hand, the penalty for making a confident guess on a correct label should be 0, right? So without explaining too much, we can just use the ln for this, the ln function, right? Because ln will tend to infinity as you get to 0, and tend to 0 as you reach 1. Right? So you can fiddle with this a bit. Right? You just throw your sigmoid function into the ln, and in fact, it's going to give you the error. I don't want to describe it too much because I don't have much time left. Slide 27 of 49. There's no way we're getting into neural networks today. I can get you halfway there, so maybe we can do the other half later. Right, so you have the sigmoid you take the ln of the sigmoid, you take the ln of 1 minus your hypothesis function, and that gives you cost. Right? So maybe you don't need to understand this too well. All you need to understand is that if you want to separate data, you have to form some boundary between those two things. Then you give the distance to the boundary from any of those points to the sigmoid function, which assigns you a probability, which then you throw to the cost function, which gives you the cost of assigning that probability. Right? It's like the linear regression, except like, I don't know, the things I'm saying are a little bit more complicated, but fundamentally it's the same thing. Right? You're training parameters of a line, you're associating a cost for setting those parameters, and then you're minimizing the cost. Right? In the first instance, it was easy because we're just fitting some points. In this instance, it's a little bit more sophisticated because we're getting a probability function. This is the one slide that you need for implementing the cost function. I don't want to talk about it too much because I think what I said is enough to keep going. Okay, so now I need to tell you how to do gradient descent over that cost function. And it's a little bit more squirrely this time, right? It's not as simple as a line. So here's a proposition. The gradient of this is that. I'm not going to prove it, because who cares, right? The gradient of this is that. You can do it next year. Now, the gradient descent for this is exactly the same, right? So this is fun. You just have to make one gradient descent algorithm and give it different functions every time you want to run it. Okay, so having fully understood all of the mathematics behind this and implementing it properly, I can run this on my computer, right? So I just put a flat line in here. There's a line that's lying on the x-axis. And the cost function is saying, well, this is a pretty shitty decision boundary. Its cost is 72. One step of gradient descent. Okay, this is a better boundary. The cost of selecting this boundary is 16. That's 50 iterations later. So now things are going kind of slower. 100 iterations later, it's moved further. It's saying, okay, cost 13. 150 iterations later, we finally divided the set. But this isn't the best. You'd expect some type of equilibrium, right, of your line between the two categories. 200 iterations later, 250 iterations, 300 iterations, 350, 400, 450. Right, so no change between 400 iterations and 450 iterations. Right, so I call this stable. And your error associated with that is 5. You're generally never going to get perfectly zero error, right, unless your data is like perfect. Right, unless you will get zero error only when the data that you're given has been artificially constructed to fall exactly onto a line. Okay, neural networks. Maybe. So, what happens if the things aren't separated by lines? Right? What happens if, like, all the stuff in the interior of a circle is one category and the exterior of a circle is another category? Truth be told, you already have enough tools to solve this problem because you can simulate a higher order polynomial as a line. Right? You just have to say, so if you have 3 linear variables, x, y, and z, we just sort of all agree that z should be the x squared term. And that's all that's required. Right? You just have to assume that the positions are representing different things, right? So you could, in fact, learn a circle, because a circle is what? It has y squared and x squared. So you just need linear terms for the constant term x, y, xy, x squared, y squared. So you need 6 linear terms to simulate a circle. So you can do it, right? I could do the exact same thing I did on the last slide with some changes, and I could learn that circle. The whole point of the neural network, okay, so if I were to do this with only the techniques that I showed you, terribly inefficient, terribly slow, the number of linear terms that you need for representing even nominally large polynomials, it's explosive. The reason we have neural networks, basically, is because they are effectively a practical way of implementing logistic regression for higher order polynomials, right? So the decision boundaries that we were working in logistic regression were simple lines. The decision boundary that a neural network can draw is an arbitrary shape, basically. Not quite arbitrary, you can't loop back into yourself. It has to be a parameterizable curve, basically. I don't know if you know what that means, but who took physics? Do you know what a space curve is? No? Okay, so you basically can get any decision boundary you want with a finite number of exclusions from that. You can't do crazy things like crossover, but that's essentially what a neural network is going to do. I'm giving you some data points that exist in some crazy high dimension, and I'm saying, can you please learn a decision boundary which categorizes these data points in higher dimensions? You're going to be made to be quite familiar with graphs like this. Graphs, networks. Right? Your whole life as computer scientists you're going to be buried in these type of graphs. So a graph is this collection of nodes, the circles, connected by edges, the lines, with weights on them, the things that I stuck on the lines. So this is how I would represent a neuron or a node in a neural network. And it's called a neural network because we're basically simulating the same stuff that happens in our brains. Right? Your brain is a very powerful wet computer with amazing pattern recognition capabilities. Right? You can distinguish a 3 from a 7, a cat from a dog, trees from humans. Right? Computers can't do that, or they can't do it quite well yet. So this is why this is called a neuron. How much time do I have left? 2 minutes. If you give me 2 minutes, I can show you a neural network. This is a node representing linear regression. Right? Remember I said you have to give me a weight. You have to basically define the line by giving me the appropriate intercepts and slopes and an input. So all this represents is the input. The x's are the input. You send them through with a weight, right? So I'm just basically saying this is representing theta 1 times x1. Right? And then this comes out. Right? So this is just how you would draw linear regression. This is how you would draw logistic regression. Same thing. You have some input, which gets weighted, which gets sent to the sigmoid function, which gives you a probability. Right? So this is just a visual way of denoting all of those equations I showed you. Now, this is a circle. This is a node that's spitting something out. Right? Thereby, I can connect up more stuff. Right? So this is a single layer neural network that does the categorization for the digits. Right? Because remember, all I gave you was the power to say, this is a 2 or not. This is a 3 or not. You could stick all of those individual logistic regressions together to like get something that will actually tell you this is a 7. Right? By looking at the individual probabilities, right, of being a 7 or not, and then choosing the max one. So neural network, right? For doing labeling handwritten digits. A more complicated neural network, right? This is a 3-layer neural network this is a 5-layer neural network with 3 hidden layers, right? But fundamentally, all this is telling you is the rule for determining this value, right? Because you're saying this is a number which gets weighted and gets sent to these nodes. And this is a node which is accepting weighted inputs from the thing before it. So I'm basically just doing like individual linear and logistic regressions on those nodes. This is the one slide which tells you how to formulate everything I told you as matrix operations. This will go on the web, so don't worry about taking pictures. Okay. So, the last thing I want to tell you is that you can evaluate this network. You can give it the x1, x2, and x3 and push everything forward to get the output. Once you get the output, you have a guess. And then you could say, what was the error of choosing this guess? And it turns out there's something called back-propagation, which is not only tells you the error, but helps you correct everything, right? Because, let me see here. Okay, who cares, right? So if you're in this network and you get to the end and you have a value and you're like, this is wrong, I can say, well, how wrong is it? And how much of the error came from this node? How much of the error came from this node? How much of the error came from this node? And given that there's some error in this node, how much error was contributed from the node before? And then you say, well, adjust the weights so that things producing a lot of error get minimized. Right? To punish the things that are creating error and promote the things that are leading to good results. And if you throw this thing a ton of data and let it train itself, that's it. That's a neural network. That's how you can get something to detect a bird, right? By showing it 8 million pictures of birds and another 8 millions of pictures of it, not birds. And then it'll just train theta. That's it. Congratulations, you know what a neural network is, and machine learning, and artificial intelligence. So it's not that mysterious. It's just linear algebra, basically. High-powered linear algebra from the 70s that was given a sexy name. So you guys enjoy your Thanksgiving. 31 degrees tomorrow, by the way, so don't forget to bring some shorts home. Okay. I'll see you guys after the break. Feel free to email me if you need to, with questions, not like for hello.